And we might just have a look at a last application of it as well to finish off, okay? So first of all, coming back to some properties of the transform. Focused, autofocus. Okay. Suppose we have functions f and g with transforms capital F of s being the Laplace transform of the function f, and capital G of s being the Laplace transform of the function g. So we've got two functions which have transforms capital F and capital G. Now remember that the Laplace transform of the product function f of t, g of t is not capital F of s times g of s. Okay, I warned you about that when we first started looking at the Laplace transform, and well, the basic reason why is that integration is not multiplicative. Integration is not multiplicative like this. I.e., the integral of the product of two functions x of t times y of t dt is generally not the product of the two integrals, integral x of t times the integral y of t. Okay. If it was, I mean, if integration did behave like this, or something like this, then, well, still not exactly, but, you know. Integration does not behave like that. It is linear, though, so the Laplace transform of the sum of two functions, or the general linear combination of two functions, is the linear combination of their respective transforms. But what we'd like to ask ourselves now is, can we make sense of this product function, f of s times g of s, and how it might relate to f and g? Question. So we're asking ourselves that. So rather than write up the result and then prove it, we'll do a bit of investigation of it and discover the result as we go. Okay, so we're going to have a look at this product, capital F of s times capital G of s, okay, which is the product of these two Laplace transforms. So they're both Laplace transforms, so we can write them both as the integral from 0 to infinity of minus s times sigma, say, f of sigma d sigma. And why am I using sigma? Well, I'll explain why I'm using sigma in a moment. And this is multiplied by the integral from 0 to infinity e to the minus s tau g of tau. So I'm just using, I don't want to use t as the variable of integration, because I'm going to end up with an integral in terms of t. Remember, these are just variables of integration anyway. But this first thing here we recognize as the Laplace transform of capital F, of little f, the integral of the exponential times f over the range 0 to infinity. You have e to the minus s times the variable times f of the variable. And the same thing here for g. So these are the Greek letters sigma and tau I'm using. So at the moment, this is just the product of these two integrals. but they're both depending on different variables. So I'm free to multiply them together, or to turn them into a repeated integral, which will look like something that we encountered when we were looking at multivariable calculus. Okay. So we're going to express this as the integral from 0 to infinity. So we're going to make the outer integral be d tau with respect to tau. And then we'll have an inner integral 0 to infinity. And this will be f of sigma. And we'll collapse the two exponentials together. So this is sigma plus tau, d sigma. And I'll leave the g of tau on the outside here. Okay, so now this, what was the product of two integrals, I'm now writing as a double integral, one integral inside the other one. Okay, and the observation we make here is again kind of what we did before when we're doing some of these properties of the transforms. We make this observation that this inner integral here is almost looking like a Laplace transform. It's the integral of this function times the exponential from 0 to infinity. So we try and we try and fix it up. Okay, so we'll make a substitution. I'll introduce my new variable t now as sigma plus tau. So that will allow me to put a t up here in this variable of integration up here. Sorry, into that exponent position up there. So I'm leaving the outside integral, which is with respect to tau. I'm leaving that alone. And I'm changing this inner integral. So when sigma is 0, this inner integral starts at the value tau. And when sigma goes to infinity, it goes to infinity. And instead of f of sigma, I have f of t minus tau. And then I have e to the minus st. And d sigma is equal to dt. So we're performing this substitution within the tau integral. So tau is considered a constant for the purposes of the inner integral, where we're making this substitution. As far as the inner integral is concerned, the variable tau is just a constant, okay? Because the integration of tau is done on the outside of this integral. Remember, that's how we dealt with these repeated integrals when we were doing integration of functions of two variables. We thought of the outer integral as kind of supplying the parameter of its variable of integration, kind of supplying that as a parameter to the inner integral. I've still got my g of tau here. Neglected to put that in. And I can now rewrite this by sending the g of t or g of tau factor inside and putting that beside the f. And now we've kind of made some progress. We've got our e to the minus st factor, which is going to become the exponential factor which is involved in a Laplace transform at the end. And we've got these functions f and g beside each other. Now, it's not quite the product function. They aren't evaluated at the same argument, but their arguments are related. They're, t minus tau and tau. So the two arguments are related by a fixed kind of shift, or there's a relationship between the two arguments there. They always sum to t when you add them. But now at the moment the t integral is on the inside. But in order to recognize it as a Laplace transform, we'll want to change the order of integration to put the variable on the outside. So you could say, in order to move towards a transform, i.e. something which looks like some kind of integral dt, we'll change the order of integration. Now, if you sketch what's happening to how these things are integrated here, if we've got two, I don't think it matters. I've got a t-axis and a tau-axis, and we've got this line t equals tau. At the moment, so what region in the t-tau plane am I integrating over here? Well, tau is going from 0 to infinity, and for a given value of tau, the inner integral t goes from tau to infinity. So I'm integrating over this kind of infinite triangular region here. So it's this half of the first quadrant. Okay. So tau is going from 0 up to infinity, and for a given value of tau, the t variable on the inner integral proceeds from tau up to infinity. So if I want to change the order of integration, my outer integral becomes the t integral. So again, we do see parts of this region at every t value from 0 to infinity. But for a given value of t, here, between what limits do we integrate on the tau variable? Well, we only integrate to cover that vertical strip there. So from the value tau equals 0 up to the value t, okay, which is the value of tau corresponding to the point on that line. And we have f of t minus tau, g of tau, e of minus st, d tau. And we'll just do one last manipulation, is to now recognize that this exponential factor, now e to the minus st, it's independent of this variable of integration tau here. So it can move outside. Or indeed, we'll move it to the front. And that will look like our original definition of the transform. So everything else remains the same. And if you think about it, it's finally now looking like a Laplace transform, looking like a single Laplace transform. Okay, because here it is. It's an integral with respect to the variable t from 0 to infinity, e to the minus st times this function of t. Now, it mightn't look amazingly like it to you to begin with, but this integral here is a function of t. Because t is there as a variable, it's the upper limit of integration for it. Okay? And this tau, well, this tau is neither here nor there because it's integrated out, okay? So this is an important function of t here. So we'll call this our h of t. So this is the Laplace transform of this function h of t. This function is a very special name. This is called the convolution function. So the function h is called the convolution of f and g. Oops. So what did this start? What was on the left-hand side of all these equations up the top was the product of the Laplace transforms of f and g. So the product of the two Laplace transforms is the Laplace transform of the convolution of the two functions. So when you multiply together transforms, the equivalent operation with the original functions is to convolve them, or the convolution of the two. Which is, it's a type of product, because you're forming these products, a value of f times a value of g. So it's a kind of product, but you're summing up all these individual products where you're evaluating them at complementary arguments, such that the arguments always sum to the value t. So it's some kind of a strange mixture or product which kind of takes account of all the values of the two functions from 0 up until the current time. Okay, it's the convolution of the two functions. So this, remember, is what corresponds to, or it's the when you multiply together the Laplace transforms, that is the Laplace transform of the convolution. So, okay, everybody got that page? I'll put the scans up as normal on the G+ page. So a couple of other exercises for you to try. You could bring these to the tutorials this week. I'll send them on to Stephen and Andy. Perhaps tell them you're going to have a look at these. Is to establish a couple of other properties. So if the Laplace transform of a function f, if we write it as capital F of s, as we normally do, so here's a couple of properties. What is the Laplace transform of the function f where you rescale the argument by a certain amount? Okay, so here we're rescaling the argument by some amount a. So we still think of this as a function of t, but a is some parameter. Well, this is going to be a times f of a of s. I think. Yeah. And the second property, so this is for, think of a being a positive quantity there. So if you rescale the argument of the function f by some amount a, that is the effect you're going to have on the Laplace transform. Now this is kind of an example of the, well, you can see this as a special case of convolution, if you like, or prove it on its own, that if you take the Laplace transform, not of the original function f, but of its integral, all the way up to the value t. So you're summing up all the values of the function f from 0 to the current time. This is going to be equal to 1 over s times f of s. Well, this is a special case of the convolution. Special case of the convolution result, or this is kind of what I have in mind, is to prove it using integration by parts. Okay, so if you have a go at these for the tutorials, just other little exercises. They can both be proved by going back to the original integral definition of the Laplace transform, the integral of e to the minus st times whatever the function is, dt. And this integration by parts one is kind of nice. You need to have some good handling of coping with an integral inside another integral and using. You also want to use the fundamental theorem of calculus. Will also you'll need to refer to there. Fundamental theorem of calculus. Is that right? Calculus. Yeah, I think so. Yeah. Maybe. Yeah. Okay. So I'd like to finish then by going through showing you an application of these, or one class of ODEs that are amenable to solution by this Laplace transform technique. Has everybody got that page? Yeah. So this is in the area of spring and mass systems with damping. So spring and mass systems with damping. Now, what kind of things go? There's some ingredients into these kind of things. So it's the motion of masses, perhaps in a gravitational field. So following what happens to a mass when you let go of it here near the Earth's surface. Springs. There's a simplified diagram of a spring. Suppose this spring is, suppose it's at its equilibrium. Okay, so it's just sitting there. It's neither stretched or under compression. It's just sitting there in its natural, stable state. A spring is characterized by its stiffness, K. So this is some parameter which characterizes the property of the spring. And if x is the displacement think of one end of the spring as being fixed or so on. But if x is the displacement of the length of the spring, beyond the equilibrium distance, beyond the equilibrium length, then the spring exerts a force of F equal to k times x. All right, k times x or minus plus, let's go minus. It's going to be minus k times x. So if you try and stretch the string, so if we increase k in the positive direction, obviously when you try and stretch a spring, it pulls back. It wants to go back to its equilibrium length. And the force that it gives is proportional to the displacement. And this proportion is this characteristic of the string is called the stiffness. Or if you try and compress the spring by shrinking it lower than its equilibrium length, so you're making x negative, then you'll get a force which is negative, negative. You'll get a positive force because the spring will push against that. It will want to go back to its equilibrium length again. The other component of such systems are dampers, which are devices that are used to, as they say, to dampen the movement, of the system. And these are characterized by a damping coefficient B. So in some ways you can think of these as kind of like it's some kind of a or an air-filled chamber, but the one end of it can move. It's not quite airtight. There's like a tiny valve allowing the air to pass in and out of this, but the hole would be very small. So if you try and push the end into the pot, you know, it's kind of hard because you have to push against all the air that's in there, and the air has to squeeze out. But equally, if you try and pull this left end out of the pot, that's quite hard as well, because when you pull, you're creating a vacuum, or you're creating lower pressure air in there. You're essentially pulling against the atmosphere outside. And so the air has to flow back into the pot through this tiny hole. That takes time. So it resists whatever force is applied to it. If you try and push the left rod into the pot, it resists that. Or if you try and pull it out of it, it also resists that. So the force that this kind of thing exerts, but its characteristics is that the force is proportional to x dot or x prime, the derivative of the displacement. So it depends how fast you try and push the left rod into the pot or pull it out of it. The resisting force it sets up against that is proportional to the velocity. So it's a different kind of characteristic to the forces that the spring exerts. Okay, so what's a kind of a little application or a little, an example type problem that we could analyze with this? So here's an example problem. I've taken this is one of the books on the reading list for the course. It's Modern Engineering Mathematics. It's by Glyn James. You'll find it in the library block on the Moodle area. It says if you look in chapter 11, you'll find these kind of things. So this example problem is the landing gear of a dropped space probe or something. You want to drop some device onto the surface of a planet. Okay, if you just drop the thing, it smashes into pieces. That's no good. So you need some kind of a landing gear. So not a kind of a landing rocket, just some kind of mechanical suspension kind of system that you're just going to drop the thing, and that will cushion the forces as the thing lands. So a simplified diagram, or a diagram of a simple one of these, is you have a large mass, which is the mass of the probe, or the device, the robot you're dropping down onto the planet. And it has a spring, which is connected to some kind of landing foot that's going to impact on the planet. But if you just had a spring and you drop the thing, it's going to go bouncing all over the place. So you want to control stop it bouncing around too much, so you have a damping pot on it as well. So this combination of the spring and the damping pot, so the spring absorbs some of the force of impact, but the damping pot stops the thing just starting to bounce around wildly, because if you try and compress the damping pot or try and stretch it out, it resists that movement as well. Okay. Now this is the positive x direction. So we'll consider this thing falling down onto the planet. Now when it's falling, the system isn't under any, well, the landing gear isn't under any force. So the landing gear is settled at some equilibrium length. And so at t equals 0, it impacts the planet, impacts the ground, and x equals the displacement from equilibrium. So obviously when it hits the ground, the mass is going to sink down, and then the spring will take over and it will bounce it up, and the displacement pot is there to resist all these motions. So we're thinking that it'll hit the ground and the mass will sink a bit, then return up, maybe sink a bit, but that it should settle down to some final stable resting point. Now we'll suppose that it's dropped from a height h to give it an impact velocity of the square root of 2gh, where g is equal to the acceleration due to gravity. Which we'll take to be 9.8. It's approximately the acceleration due to gravity here. I'll leave out the units from all these things to simplify it. We'll suppose that the mass is 50 kilograms. This is just some basic setup information, some typical information. The damping coefficient is 180. These are Newton seconds. Well, I'll leave out the units. And the spring stiffness is 474.5. And the basic question, or the basic task here, is to investigate the effect of different drop heights h. So what we need to do is set up a differential equation that is going to model this. And the differential equation comes from Newton's third law, which says that the forces on a body equal the mass times the acceleration. Okay. Now, the acceleration is the second derivative of x. Okay. So from t equals 0, so m times the second derivative, x double dash, so this has got to equal the forces. Now, there's three different forces operating on the mass. Okay, there's the force due to the pull of gravity that's pulling the mass down towards the surface of the planet. That's going in the positive x direction. It's pulling the mass down. But going against this is the resistance due to the spring. And so that's k times x. And the resistance due to the damping pot, which is b times x dash, which is the first derivative of x. That's our differential equation, and there's an initial value, there's initial values to it. At x equals 0, at the moment of impact, it impacts the ground at t equals 0. So at the moment of impact, the system is in equilibrium. Okay, because it's just been free falling. So the spring and the damping pot are just at their equilibrium states. And it's got an initial velocity at time 0 of, where it's here, square root of 2gh. So we've got a differential equation there, second order. So you see second derivative. And we've got two pieces of information, those two initial values, okay, for saying it's at equilibrium position at time equals 0 and what its initial velocity is, okay? So this can be solved using Laplace transforms. So you transform the whole thing. So you have the mass. The transform of x double dash is s squared times s bar, x bar, minus s x of naught minus x dash of naught. Transforming the right-hand side, m times g is just this constant. It's not changing with time, so you get m times g over s. Then you have minus k times x bar. You're transforming x. And then you have minus b times the transform of x dash, so you have s x bar minus its initial value. So then you want to put in the initial conditions. And simplify this thing. So putting in the initial values and solving for x bar, you can get a solution for x bar. So you're just putting in these initial values. So x of 0 is 0. X prime of 0 is this constant over here. And just moving everything around, solving algebraically, you see that there's two terms to the solution. There's this term here, which the observation is that it doesn't have a h in it. And then there's the second term here, which is m times 2gh all over ms squared plus bs plus k. And this square does have the h in it. So this term here comes about from the contribution that the initial velocity is making to the thing. So that comes about from this m times minus x prime 0 term over here. This term here is independent of h, we'll just remark. And this depends on h. So in particular, if h was 0, you just have this term here. So this would be the equivalent thing to just taking the probe and just placing it on the surface of the planet, not dropping it onto it, but just positioning it so that the landing gear is just touching the ground and just letting go of it. So the only influence it had, the only motion it had would be the motion under gravity. Or if you did let it drop onto the planet, so it did have some non-zero initial velocity, you then get this term coming in. Okay. So then we just solve this as usual. And we can get the equation of motion xt. Okay, but just like in Blue Peter, I've done that already. So you can do this with MATLAB as well. I don't have MATLAB here, so I just did it in Sage. So I just type in some initial values of these parameters, the m, the b, the k, and the g, the acceleration due to gravity. I give myself these symbolic variables, st and h. I'll put a link to this worksheet on the G+ page afterwards, so you can get into it and have a play around with it. I don't think I use that v0. So this, I set up this thing called quad. This is this quadratic factor here, the ms squared plus bs plus k. Just set that up. Now this x term 1, what's this? X term 1 is the inverse transform of this first term here. Because you see, it's m times g divided by s times quad. That's what we have here, mg divided by s times quad. And I take its inverse Laplace transform. So there's a command in Sage for that, inverse Laplace, and you have to name the two variables, s and t. And you can see what we get there. Well, I'll show it to you in more detail in a moment, but you get a combination of sines, cosines, and exponentials. Then I set up a variable x term 2, which is going to hold the inverse transform of this second term. Now see, this is the dependence on h in it. So I make it a function of h. This is what this def x term 2 of h. But you can see what it is. It's returned the inverse Laplace transform again of m times the square root of 2gh, m times the square root of 2gh, divided by quad, divided by that quadratic factor there. So that's just defines a function to get the inverse transform. And then I'll define this second function x here, which is going to give me the whole solution, which will be x term 1 plus x term 2. Originally, I did it like this, x term 1 plus x term 2. So here's the solution when you drop it from 1,000 feet. But remember now, x, as we did on the original diagram, x is the displacement downwards. It's measuring the amount of compression the landing system is under. but the moment x is going up the screen. So if I make it the negative, so if I return minus of all of this, I'll leave that, but I'll just plot minus x of h instead. If I plot minus x of h, then the graph will visually look like the behavior of that the thing would undergo if you did drop it. So let's look at just if you dropped it from a height of 0. So that means if you just placed it onto the surface of the planet. So obviously when you let go, the gravity is attracting the mass, so that will compress the spring. And you can see it does bounce back a little bit. It compresses the spring down to this distance of 1 and a bit meters, and then it returns a bit, and then it finally settles down, and then settles down into that equilibrium state. Okay. So this graph we're seeing here is the graph of this function here, the x term 1. So it's this sines and cosine. So the sine and cosine gives you this oscillating behavior. But you see it's all multiplied by this exponential, e to the minus t effectively. So e to the minus t, that's going to converge to 0 as t goes to infinity. So that explains why it settles out to be this equilibrium compression state of about 1 meter. So you hold the mechanism over the ground, and with the foot just touching the ground, you let go, and the thing sinks down to about a compression of about 1 meter or so. Now, but if you do give it some initial velocity, equivalent to dropping it from a height of 10 meters, say, then you can see it changes it. It drops down much further to a compression of about 2.5 meters before bouncing back a bit, but eventually settling out at the same long-term equilibrium settled state as well. Okay. So here I've done a bunch of graphs. They're all for different heights here, and I've colored them different colors. So, I'll put the minus of them there. So it looks the right way around. So you can see the effect here of dropping the thing from different heights here. So the largest height there I did was, I think, was 10,000 meters or something. No, just 1,000. So 0, 5, 10, 100, and 1,000. So the blue line is up at the very, very top is not dropping it at all, just placing it on the surface. So it just sinks down and bounces one little bit until it gets to its equilibrium. See, and they all settle down at the final equilibrium. Of course, that value of dropping it from 1,000 meters, dropping it from a kilometer, means it's going to be moving at quite a pace when it hits the surface. That compression, you see, it's going down. It wants to compress by about 20 meters. Now, that might be outside of the range of the just of the mechanical setup. That might be a valid solution. Maybe the thing just would have crashed into the ground at some compression before 20 meters. But to take account of that, you'd have to actually know the dimensions of the thing and what were the valid ranges for the compression it could undergo. Okay. This at least shows you a kind of realistic problem setup with a parameter that depends on, which controls this initial velocity. And using Laplace transforms, the inverse transforms, etc., to get the solution and to visualize the solution under different values of the parameter. Okay. So I'll publish this sheet here to the G+ page as well. So you can go in and have a mess around with it as well and try varying the damping coefficient B as well to see the effect of that, or varying the spring stiffness to see the effect of that. Okay. You make the spring stronger, you'll see these things, you'll see these solution curves go through many more oscillations before finally settling down. Okay. Okay, we better end it there for today. So we'll be starting a new chapter on Fourier series next week.